In this video, we are going to do some examples using Stokes' theorem. So let's recall what Stokes' theorem says. So if we have a vector field in three-dimensional space, and we have this surface in 3D space that has this boundary curve, then there are two integrals that are equal to each other. So I can express the circulation of the vector field along this boundary curve using this line integral of my vector field dotted with t hat. Or sometimes the way I see this written is my vector field dot dr. Well, that's going to be equal to this surface integral of the curl of f dotted with the unit normal vector. And the unit normal vector, whether it's oriented like that or into the surface, that'll be given to us depending on the orientation of the curve using the right-hand rule. So usually in a problem that involves Stokes' theorem, either we'll have an integral that looks like this, or that looks like the surface integral form, and we convert it to the other form, often if the other form is easier than the one that we start with. Okay, so back to our example. I want to find the counterclockwise circulation of this vector field. It's a 3D vector field. I have an I hat, j hat, and a k hat around the circle x squared plus y squared equals 1 on the xy plane. So let's draw a picture. Ordinarily, to draw this circle, I would just need my x and y axes, but because this is in 3D, I should draw it in 3D space. So I have my z-axis, my x, and my y. Okay, so we got all three axes. I'll draw the negative y direction, the negative z direction, and the negative x direction. Now if I draw this circle, I have this circle of radius 1 on the xy plane, because that is something like this. So it's hitting 1 here and 1 here. And when it says counterclockwise circulation, it's sort of implied that when we view this thing from above, that we are traveling along it counterclockwise. So that would be this way. So I'll draw some direction arrows here, and I'll label this curve C. So I first want to have you pause the video for about 4 minutes to try this on your own. So see if you can remember what's the formula for circulation. And my hint is we just saw it on the previous page, and then try to evaluate it. So pause it in 3, 2, 1, pause it and try it. All right, so hopefully you did that. Hopefully you paused it to try it. Let's talk about it. So I'm going to solve this in two ways. Method one is, well, circulation, that's given by this line integral of our vector field. So I can do that line integral directly. So do the line integral directly. So the line integral for circulation is the circulation equals this line integral over the curve C. I'll draw a circle through the integral because it's a closed curve. My vector field dot dr. Okay, so to do a line integral of a vector field, I have to parameterize the curve. So parameterize the curve. And we've seen how to parameterize a circle a bunch. In this case, because the radius is 1, we'd let x just be cosine t. Y is equal to sine t. And then, well, there is a z here as well. Since my circle is on the xy plane, well, z just equals 0. Z equals 0 on the xy plane. And then my domain for t is from 0 to 2 pi to go all the way around. All right. So from there, I also need to get my velocity vector. Remember, to get the velocity, we do the derivative of each of these components and put them into a vector. So that'll give me negative sine t, comma cosine t, comma 0 for my velocity. Now we're ready to evaluate our line integral. So we convert it to a regular integral where t goes from 0 to 2 pi, 0 to 2 pi, and then I substitute in my parameterization into our vector field. So for example, y is sine of t, that'll get plugged in here for this 2y. So I'll get a vector, 2y becomes 2 sine t, comma z cubed, that's going to be 0 cubed. E to the x becomes e to the cosine t. All right, and then I dot that with the velocity. So dot it with negative sine t, comma cosine t, comma 0. and then we write dt. dt. Okay, so taking the dot product, I get the integral from 0 to 2 pi. And all that's going to be left is the -2 sine squared t. Because then after that, I'll get plus 0 dt. So how do I do this integral? The -2 is a constant, so I can factor that out. So -2 times the integral from 0 to 2 pi. And you might recall that to do the antiderivative of sine squared, we need a trig identity. Sine squared is 1 minus cosine of 2t over 2. And then from there, well, this 2 and this 2, they can cancel. And then that negative we have in front, we can distribute that into the integral. And that'll give me the integral from 0 to 2 pi of positive cosine of 2t and then -1 dt. From there, we're ready for that antiderivative. I'll get 1/2 sine of 2t minus t. And then I got to plug in the 0 and the 2 pi. 0 and the 2 pi. If I plug in 2 pi into this, the first term becomes 0, and then I get minus 2 pi. Minus, if we plug 0 in, actually both of the terms become 0. So minus 0. And overall, that's just -2 pi. -2 pi, and that is my circulation here, the circulation of this vector field along this curve in this counterclockwise direction. But I mentioned we can do this another way. So method two is, well, we can use Stokes' theorem. Because what we have is an integral that looks like this, right? This f dotted with t hat. That's just another notation for writing the integral of f dot dr. I have an integral that looks like this, where c is a closed curve. Well, I can convert that to a surface integral by using Stokes' theorem. So we can use Stokes. So use Stokes' theorem. Okay, so if I use Stokes' theorem, Stokes' theorem says that our line integral over that curve, f dot dr, will be equal to a surface integral over some surface S of the curl of f dotted with the unit normal vector ds. Okay, but what's the surface here? So what is the surface? So what is the surface that this circle is enclosing? Well, maybe the most natural choice for the surface is to let the surface be this like disk that's inside the circle. So I'm going to let that be S. So S is going to be this disk within the circle. That's the surface that has C as the boundary curve. So S is that inside disk. Inside disk. All right. So from there, I need to know the curl of F. So let's get the curl of F. Curl of F. Remember, to do that, I set up a 3x3 determinant where I have I hat, j hat, and k hat on the top. Then on the next row, I have the entries of the del operator. So partial with respect to x, and then y, and then z. And on the bottom row, I have the entries of my vector field f, which we can see those from up top. That was 2y, z cubed, and then e to the x. And then remember, the way that I figure this out is I take the first entry in that top row, which is I hat. And then that's going to get multiplied by stuff where if I cross out the row and the column that's in, and I look at the smaller 2x2 matrix, I put these diagonal entries together. So the partial with respect to y of e to the x, that's 0. And then minus, put these ones together, and that partial derivative is 3z squared. So I'll get 0 minus 3z squared. All right, and now I do the same thing, moving on to the j hat. So j hat times some stuff, where I'll cross out the row and the column j hat is in. We put these entries together, that partial derivative is e to the x, minus put these ones together, and that's 0. So we'll get e to the x minus 0. And we've seen that as we do this, we alternate the signs. So the I hat has a plus in front of it, the j hat then has a minus, and then I'll have a plus after that in front of the k hat portion. So k hat times some stuff, cross out the row and the column it's in. We put these together, that partial is 0 minus these ones, and that partial is 2. So 0 minus 2. Okay, so that's my curl. We now got to dot that with the normal vector. Okay, so the curl of f dotted with the normal vector. Well, what's the unit normal vector for this surface? Well, because it's on the xy plane, either my normal vector is pointing straight up or it'd be pointing straight down. So which is it? Remember, the convention is we use this sort of right-hand rule. Because my curve is going this way, we curl our fingers in the direction of the curve. And then as we do that, if we stick our thumb up, if we were to stick our thumb out, well, my thumb would be pointing up. And that's going to be the direction of the normal vector. So the normal vector would be pointing straight up, my unit normal vector. But straight up, well, that's just k hat. That's just the vector 0, 0, 1. Okay, so for my problem, the unit normal vector equals k hat. So I got to take my curl, let's put in bracket notation. That's negative 3z squared, comma, negative e to the x, comma, negative 2, right? That's my curl. And then dot that with k hat. K hat's the vector, k hat's the vector 0, 0, 1. And if we dot them, we just get negative 2. Okay, so that's nice. This function in this surface integral just becomes constant. Okay, so what I end up getting is the surface integral of just the function negative 2 ds. I can factor that constant out and get negative 2 times the surface integral of just 1 ds. And we've seen this many times. If I have an integral of 1, it just gives me a measure of the size of this region. Well, S is this two-dimensional region, this area. So this double integral, this surface integral of 1 represents this area of that surface. So in this case, the area of that circle. So I get negative 2 times the area of that circle is pi r squared, and the radius is 1. And that gives me negative 2 pi. Negative 2 pi, and that's my answer. So I'm getting the same thing whether I do the line integral directly, or if I decide to use Stokes' theorem, I also get a negative 2 pi. And that's good. That's good that both sides of Stokes' theorem give me the same thing. Okay, so one of the key things I want to take away from this is, I personally think that using Stokes' theorem is a little bit nicer because, well, this whole thing in the integral just became a constant. And then we didn't really even have to do an integral. It just became a geometry problem. Whereas the other way, I could do it. It's not terrible. But I did actually have to work out an integral, which required trig identity, which might be a little bit harder to remember. Okay, let's do another example. So now let's say I want to evaluate this surface integral of the curl of f dotted with the unit normal vector. And then one typo, this should say ds because it's a surface integral. In fact, even down here it should say ds. ds. Same vector field as the last problem, but now I'm changing the surface. The surface is now the hemispheric shell given by this equation, and my unit normal vector points away from the origin. Okay, so let's draw a picture first. So I'll draw my axes. So I got the z-axis, the x-axis, and the y-axis. And then I'll draw the negative directions. So I got the negative y, the negative z, and the negative x. So if I don't remember what this shape looks like exactly, I can rearrange it a little bit. So I can first square both sides to get rid of the root. That'll give me z squared equals 1 minus parentheses x squared plus y squared. And if I move the negative term over to the left side, I'll get positive x squared plus y squared plus z squared equals 1. And we might remember, okay, now this is a sphere centered at the origin. R squared is 1, so the radius is 1. So, well, why is it going to be a hemisphere, though? Because if we go from this step back to this step, I'd square root both sides. And that should technically give me a plus or minus. But the fact that I don't have that minus means z, which is the square root, well, the output of a square root cannot be negative. So we're only looking at the part of the sphere where z is non-negative. So that's the top half of the sphere. So I'm going to draw that, just that top hemisphere. So I'll draw this kind of like circular base of the hemisphere. Okay, that circular base. And then the top, that top of the dome. Okay, so here is our surface, my surface S of this hemisphere. So, well, one way I could do this, method one is we have this surface integral. We could do the surface integral directly. Do the surface integral directly. So in my function, I got to do the curl of f, which we actually worked out already. So the curl of f, and I need to dot that with my normal vector, which we'll have to think about. But the curl of f is negative 3z squared, comma, negative e to the x, comma, negative 2. That's my curl of f. We got to dot that with the unit normal vector. We've seen how to get the unit normal vector to a sphere before. The vector that's perpendicular to the surface is going to be if you connect the origin to a point on the surface. And if I call this point x, comma, y, comma, z, as a vector, this is x, comma, y, comma, z, that vector. And so I could be talking about a normal vector that's sort of pointing like this. That would be the vector x, comma, y, comma, z, or into the sphere like this. Because it tells me that the normal vector points away from the origin, it's this vector that I've drawn. I now need to make it a unit vector. So as a unit vector, n hat becomes that radius vector, x, comma, y, comma, z, divided by its length. Square root of x squared plus y squared plus z squared. Okay, and well, I know x squared plus y squared plus z squared equals 1. So on the denominator, I'm going to have square root of 1. The other way I could figure that out is, well, the radius of the sphere is 1. So this whole denominator should have just been 1. Regardless, my normal vector is just x, comma, y, comma, z. So I'm going to write that here. My normal vector is x, comma, y, comma, z. So now if I take the dot product, I'll get negative 3z squared times x, comma, negative e to the x times y, comma, negative 2 times z. All right. So, okay, so this is not the nicest looking result of the dot product. Oh, okay, and I realized I made one mistake, which is when I do a dot product, it shouldn't be a vector, right? I should be adding these things. So when I add these things, it really should have been, it would have given me minus here and then minus here, right? Because it's plus a negative, which becomes a minus. So that's my dot product. But the issue with this is, in the last problem, once I did the dot product, we got a constant. But in this problem, this dot product isn't a constant. So I have to do a general surface integral, which we could do. It's just more difficult. So, okay, so we could do this. It's just kind of tedious to do it. So method 2 is, what if we use Stokes' theorem? So use Stokes theorem to convert this surface integral to a line integral over the boundary, to convert to line int. So with Stokes' theorem, we convert this surface integral of the curl of f dotted with this unit normal vector to a line integral over the boundary curve. But the boundary of this hemisphere, well, that's this circular base. That's that circular base. I'm going to call that circular base C. What's the direction I should be traveling around it? Like the counterclockwise like this or clockwise? Well, I know my unit normal vector is pointing upwards and out. I know my normal vectors are pointing sort of up and out here. Up and out. All right. So we've seen that with the right-hand rule, if I curve my fingers along the direction of the path, if I was going this way and then I stick my thumb out, well, if my fingers were curving this way, my thumb, if I stick it out, would be like this. Oh, and that is in the direction of this unit normal, pointing upwards. So that means I'm traveling along it in this direction. So let's use Stokes' theorem. Let's convert this to a line integral. So that'll give me the line integral over that closed curve, C, my vector field dot dr. Okay, so in other words, I'm doing the line integral of my vector field over this boundary curve. That boundary curve, that's just that circle of radius 1 in the xy plane. Well, that's literally what we did in that last example. Same vector field, that's what I'm working with, over this circle in the xy plane. We did that already. That's negative 2 pi. Okay, so that's nice. All right, so let's use that. So we did this in the last example. We did in previous example. And when we did that, we got negative 2 pi. Negative 2 pi. So I won't work it out all over again because we did it already. So that gives me negative 2 pi. Okay, awesome. So that's one way I could do this. There's actually a third way we could do this problem. So method 3. Method 3 is, this is going to involve using Stokes theorem, but in a slightly different way. Use Stokes theorem to find a surface with the same boundary curve. To find a surface with the same boundary curve. Because what Stokes' theorem says is that an integral like this over a surface should be equal to a line integral like this of the vector field over the boundary curve. But no matter what the surface is, as long as it has that boundary curve, it's going to be equal to this integral. So even if I had some other more complicated surface, as long as it has this curve as the boundary curve, that surface integral is going to be equal to this thing. So those two surface integrals would be equal. So is there a simpler surface I can identify in this picture that has this curve as the boundary curve? I want to have you pause the video for 1 quick minute to think about that. Can you find another surface, simpler one, in this picture with the same boundary curve C? So pause it in 3, 2, 1, pause it and try that. Okay, so hopefully you thought about that. Let's talk about it. So I'm going to draw my axes again, my Z, my X, and my Y. It's X, Y, and Z, and then I'll draw the negative directions. So negative Y, negative Z, and negative X. And then I'll draw that boundary curve. So that boundary curve, that circle of radius 1 in the XY plane, centered at the origin. So our boundary curve, which I'm calling C, well, yeah, there's another surface with that same boundary. That's this internal disk, which actually we were working with in the last example. Maybe let me call this S star. Okay, so what this means is, if I want to do my surface integral over my hemisphere of the curl of F dotted with the normal vector, well, Stokes' theorem says, well, that should be equal to this line integral. That should be equal to the line integral over that boundary curve of my vector field, dot dr. But then if I use Stokes' theorem again, this should be equal to the surface integral over the new surface, which we're calling S star, of the curl of F, dotted with the normal vector to this new surface, ds. Oh, and I forgot to write ds for my surface integral here, and I should write ds for this one. Okay, so, well, what's the normal vector to this new surface? Well, either I could draw it straight up like this or straight down. So which way is it? Well, because I know I'm traveling along the curve this way, I use that right-hand rule. If I curl my fingers in the direction of the curve, and then I point my thumb out, well, it's going to be pointing up. So that means my normal vector that I want here is pointing straight up. So my normal vector, if it's pointing straight up in the z direction, that's k hat. So, okay, this normal vector is k hat. And now this becomes exactly the problem that we did here. In the last example, we did the surface integral over this internal disk, right? That's what we did here. We did the curl, we dotted it with k hat, we got -2, and then we did that surface integral, and that ended up giving us -2 pi. Okay, so we did this already. So we did this in the last example. Did in the previous example. Did in the previous example. And when we did that, we also got -2 pi. Okay, so these examples illustrate some of the power of Stokes' theorem. The two most common ways we'll see it used are, we typically might be given an integral in this form, and if it's more efficient to evaluate it as a surface integral, we might do that. Or if we're given a surface integral in this form, we might choose to do it as a line integral over the boundary curve instead.